Friends, today we are going to discuss about the preparation for the Neet. We consider the numerical what are the asked in last year. That means in past year, what are the questions asked? We are going to try to solve it, and I give the hint to solve this numerical and try yourself. If you have any question, so write down in notification. Now listen, this question is asked in PMT 1988. What is given? Focal length of a convex lens in A. Chapter 9, Ray Optics, right? Focal length of a convex lens in A having the effective index of material 1.5 is 2 centimeter. That means in A medium, the focal length is given, that is the 2 centimeter. Okay. If this lens is immersed in a liquid of effective index 1.25, here the effective index of a material is given, right? That is the 1.5 for a glass. Ng is given as 1.5. Now effective index of a liquid is given 1.25. We have to find out the focal length of a lens in a liquid. FL we have to find out. Here for a convex lens, radius of curvature are not given. So we have the equation of lens maker. Right? From lens maker's equation in A medium, 1 upon FA is equal to Ng minus NA upon NA into bracket 1 upon R1 minus 1 upon R2. That is our equation 1 in A. And in liquid, the focal length is 1 upon FL is equal to Ng minus NL upon NL into 1 upon R1 minus 1 upon R2. So we write the equation of the focal length of a lens in A medium and also in liquid by using the lens maker's equation. But here R1, R2 are not given. We require the value of Fn. Fa given, Ng given, right? Okay. Na, there is the effective index of A medium, that is 1. Na is equal to 1 for A medium. So how we find out it? By taking the ratio of equation 2 to 1. Therefore, taking ratio of equation 1 and 2. 1 to 2. Therefore, our final equation becomes FL upon FA is equal to this divided by this. Okay? Therefore, Ng minus Na upon Ng minus NL into NL upon Na. Substitute the value. Ng 1.5 minus 1, 1.5 minus 1.25, 1.25 upon 1. So we obtain the focal length of a lens in liquid is 5 centimeter. Is 5 centimeter. Again, read the question carefully what is given. The focal length of a convex lens in A medium is given Fa, 2 centimeter. Having the effective index is 1.5. That is the effective index of material of a glass lens. Okay. Now the lens is immersed in a liquid having the effective index 1.25. Find the focal length of a given lens in given liquid. For that purpose, we are using the lens maker's formula. Clear this? Okay. After that, the second, here the 5 centimeter is the answer. After that, the next question is, for a small prism of a prism angle A, 1A incident on one side of the prism at angle I. That means the angle of incidence is I is given. And emerge out from other side perpendicularly. Therefore, figure becomes like this manner. There is the small prism is given, having the prism angle is E. That is the perpendicular to the surface, both sides. So what's happened here? One ray of light is incident on the prism at angle of incidence I. So here the ray of light is going from A medium to the here N1 is equal to N1 is equal to 1 for A medium, and here the N2 is equal to 1. So ray of light is traveling from here to the denser medium. So here the phenomena of refraction take place. So this incident ray is refracted. Therefore, there is incident like this way. That is the angle of refraction I1. But this reflected ray is incident on the other surface of the prism perpendicularly. Therefore, there is emerged out perpendicular to this surface, 90 degrees to the surface. Therefore, here the angle of emergence is 0, and here the angle of incident for the second surface R2 is also 0. For a prism, we know that R1 plus R2. R1 plus R2 is equal to prism angle A. But R2 is equal to 0. Therefore, R1 is equal to E. Now, applying the Snell's law. Applying Snell's law at this point. Therefore, N1 sine I is equal to N2 sine R1. N1 is 1 for A medium. Therefore, sine I is equal to N2 is equal to N. And here sine R1. But from this equation 1, R1 is equal to A. Therefore, sine I is equal to N sine A. But prism is very small. Therefore, angle of incidence is very small and prism angle is very small. Therefore, I is equal to mu. I is equal to mu. So there is our answer C. So this numerical is also asked 2 times, 1989 and 2012. So very easy numerical if our concept about the theory is clear, so we can solve it. Now third numerical, a ray of monochromatic light enter in a medium of refractive index 1.5 from vacuum. Then wavelength of refractive light is, what should be the effective wavelength of refractive light? One ray of light of monochromatic light enter from vacuum to the denser medium, having the effective index is 1.5. So the wavelength of refractive light is increased because constant or depends on intensity of refracted ray. This question was also asked 2 times, 1991 and 1992. Now we know that refractive index, from the definition of refractive index, N is equal to C upon V. C is the velocity of a light in a vacuum, while the V is the velocity of a light in a given medium. But we know that C is equal to F lambda and V is equal to F lambda dash. Frequency of the light does not change if the medium is changed. Therefore, N is equal to F lambda upon F lambda dash. Therefore, FF cancel. Therefore, N is equal to lambda upon lambda dash. Lambda upon lambda dash. Therefore, new wavelength lambda dash is equal to lambda upon N. N is given 1.5. Therefore, new wavelength lambda dash is equal to lambda upon 1.5. 1.5, 3 by 2, therefore 2 lambda by 3. Therefore, lambda dash is always less than the wavelength of incident light. Therefore, lambda dash of the wavelength decreases. Wavelength decreases. Clear this? Okay. Again, keep in mind that from the definition of effective index, the ratio of light in a vacuum to the given medium, that is known as the effective index of a given medium with respect to the vacuum. And that is known as the absolute effective index. N is equal to C by V. We are using this concept when we derive the Snell's law. Okay. But we know that C is equal to F lambda. That is in vacuum. For given medium, V is equal to F lambda dash. The frequency of the incident light does not change with the change in medium. Substitute in this equation. So N is equal to F lambda upon F lambda dash. FF cancel. Therefore, N effective index is equal to lambda upon lambda dash. Therefore, new wavelength lambda dash is equal to lambda upon N. N is given 1.5. Therefore, 2 lambda by 3. Therefore, new wavelength is less than the wavelength of incident light. Therefore, wavelength decreases. Clear this? Okay. Now, next is fourth. The green light of wavelength 5460 angstrom. That is given 5460 angstrom. If incident on a glass slab is in a medium, if the effective index of a glass is 1.5, N is equal to 1.5, then wavelength of a light in a glass slab that is similar to the earlier that is also asked in 1991. Right? The same equation we are using directly. Effective index N is equal to, we require the lambda dash. Now, the effective index N is equal to C by V. Therefore, F lambda upon F lambda dash. Therefore, lambda upon lambda dash. Therefore, lambda dash is equal to lambda upon N is equal to lambda upon 1.5. Therefore, 2 lambda by 3. Therefore, 2 lambda 5460 upon 3. Therefore, we obtain 3640 angstrom. So directly we are using this equation from the concept of definition of effective index. N is equal to CV. And if we directly know that N is equal to lambda upon lambda dash from earlier equation, earlier numerical, so directly we can apply it. Therefore, the wavelength of a light, green light in a glass slab, lambda dash is equal to lambda upon N. So that is the 3640 angstrom. Clear this? So very easy numerical. Right? First, keep in mind that what is given and what we need to find out. What are the equations showing the relation with given quantity and the required quantity? Clear this thing? Okay. Okay, now next numerical is that there is asked in 1992 and 2018. A prism of effective index of 2. Right? Here we also note down n is equal to root 2. And prism angle is 30. Prism angle is 30. Having the one reflecting surface is polished. 1A of monochromatic light is incident on one surface, then reflected, and this reflected A is incident on a surface by one surface, then it reflected on the same path from the polished surface. Then angle of incidence per ray is, now what this figure suggested there, we have to find out the angle of incidence. Our figure is like this manner. Here the one prism is given. Then the prism angle is small, that is the 30. One surface is polished. This surface is polished surface. There is the prism ABC. There is the perpendicular on AB surface. One ray of light is incident like this way. Angle of incidence is this I. Ray of light is incident on the one surface, then there is the reflected. This reflected ray incident on the polished surface, and then after the incidence on polished surface, there is the reflect back on the same path. There is the reflected back on the same path. Then, what is the angle of incidence? Earlier we discussed the same numerical, our second numerical. Here the polished surface is not given. Here the A is immersed out perpendicularly to the other surface. Here the same equation we are using. Right? Okay. Therefore, the angle of incidence here I1 plus I2 is equal to A, but I2 is equal to 0. Because whatever the reflected A, there is the incident perpendicularly. At that time, there is the reflected on the same path. Therefore, I2 is equal to 0. Thus, I1 is equal to A is equal to 30 degrees. Now, applying Snell's law, here the refractive index N1 is equal to 1, here N2 is equal to N. N is given root 2. Okay. Now, N1 sine I is equal to N2 sine I1. N1 is 1, therefore sine I is equal to N2 root 2 sine 30, because the I1 is 30. Sine 30, 1 by 2, root 2 into 1 by 2. That means there is the 1 upon root 2. Sine I is equal to 1 upon root 2. For 45 degree, its sine value is 1 upon root 2. Therefore, I is equal to 45 degrees. Therefore, the angle of incidence is 45. Again, here first understand the question what is given. One surface of a small prism having the prism angle is 30 and effective index is root 2. One surface is polished. One ray of light is incident on one surface, then there is the reflected. This reflected ray incident on a polished surface and reflected on the same path. Reflected on the same path, therefore I2 is equal to 0 here. Prism angle is given, I is given. Effective index of A medium is 1 and material is given root 2. So first from equation I1 plus I2 is equal to A, but I2 is equal to 0. Therefore I1 is equal to A is equal to 30. Now we are applying the Snell's law at point of incidence. That is the P at Q. Therefore, N1 sine I is equal to N2 sine I1. That is the I1. This angle is I. I2 is 0. Now n1 sin I is equal to n2 sin I1. Therefore n1 is 1 for A medium. Therefore n2 root 2 sin 30 sin 30 1 by 2. Therefore 1 upon root 2. Sin 45 has the value is 1 upon root 2. Therefore angle of incidence is 45 degree. Clear this? Okay. Now the next, effective index of a glass is given 1.5. N is given the 1.5 for a glass. The sunlight passing through this glass of thickness B over the T. B is 4 millimeter. Convert into meter. So 4 into 10 is 2 minus 3 meter. How much time taken by the sunlight to pass through this glass having the thickness is 4 mm? This question you also asked here, 6 mm or the 5 mm is placed. Okay. Now listen, this question is asked in 1993. Okay. So we know that the effective index Cn is equal to C by V. The effective index N is equal to C by V. But we know that V is equal to, from this equation, C by N, and also we know that the V is equal to distance upon time. Distance upon time. Therefore, distance here we consider as a thickness. Therefore, B upon T. Therefore, T is equal to B by V. Therefore, B by V. Substitute the value of V from this. Therefore, T is equal to B upon C upon N. Therefore, N B upon C. N B upon C. N is given 1.5. B is the thickness. 4 into 10 is 2 minus 3. C is the velocity of a light in a vacuum. 3 into 10 is 2, 8. So here 15 for the 60, 6 by 3, that means the 2 into 10 is 2 minus 11 second. That is the answer. Again, here we are using the concept of effective index N is equal to C by V. But we know that velocity is equal to distance upon time, here thickness upon time. Okay, from equation 1, this equation 1, V is equal to, then C upon N, substitute here, C upon N. N is denominator comes into the numerator, therefore N B upon C. N is given 1.5, B, 4 mm, 4 into 10 is 2 minus 3. C, speed of a light. 3 into 10 is 8, therefore 2 into 10 is 2 minus 11, 7. Now, next is, for a prism of a small prism angle A, and effective index N, and angle of minimum deviation delta M, the relation between them. Already we derived this equation in theory portion, because the effective index N is equal to sine A plus delta M by 2 upon sine A by 2. Now, if A and delta M are small, so we can write A is equal to A plus delta M by 2. N is equal to upon A by 2. 2 cancel, therefore NA is equal to A plus delta M. Therefore delta M is equal to A common N minus 1. When we derive this equation, N is equal to sin A plus delta M by 2 upon sin A by 2 in theory portion. After that we consider for a small prism For a small prism, that means the angle of prism is very small. If the angle of prism is small, therefore the angle of minimum deviation is also becomes the small. Therefore, A and delta m are small. Therefore, sine value of A plus delta m by 2 and sine A by 2 also becomes the small. Therefore, we consider sine is cancelled out. Therefore, n is equal to A plus delta m by 2 upon sine A by 2. Simply A by 2. 2 cancel. Therefore, n is equal to A plus delta m upon A. A taken this side. N A is equal to A plus delta m, and then delta m is equal to A into n minus 1. Clear it? Okay. Now, one object is placed at midpoint of a two plane mirrors kept at 60-degree angle. Kept at the 60-degree angle with respect to each other. So here the two plane mirrors are, that is kept at 30-degree angle, one is, and second is kept at again 30. Therefore, the total angle between these two plane mirror, that is the mirror 1, mirror 2, is 60 degree with respect to each other. And we extend this mirror in this side and this side, so this angle is 60 degree. One object is placed at midpoint between them. So how many numbers of the images formed by these two mirrors? For that purpose, keep in mind this equation, number of images is equal to 360 divided by angle theta. Here theta is given 60, therefore 3 and minus 1. 360 by 60 minus 1. Therefore 6 minus 1, 5 images are obtained. 5 images are obtained. So keep in mind this equation. How many number of images obtained? So 360 by theta minus 1. Okay. Now the effective power of a combination of convex lens of 80 cm focal length and concave lens of 50 cm focal length. Okay, here one is given the convex, second is given the concave. We know that the effective power P is equal to P1 plus P2. P1 plus P2. And also we know that power is equal to reciprocal of focal length is equal to 1 upon F1 plus 1 upon F2. Now, F2 is the focal length of concave lens. Focal length of a concave lens is always negative. Therefore, 1 upon F1 minus 1 upon F2. 1 upon F1 minus 1 upon F2. Therefore, 1 upon 0.8 minus 1 upon 0.5. Thus, we obtain the power is equal to minus 0.75 diopter. That is the answer. Here the combination of one concave and second is the convex. That means the one convex and one concave lens combination are given. Convex lens has the positive focal length, convex lens has the negative focal length. And we also know that the power is equal to reciprocal of focal length. Therefore, the resultant or the effective power of this combination P is equal to P1 plus P2. Here 1 upon F1 plus 1 upon F2. But for the concave, focal length is negative. Therefore, 1 upon F1 minus 1 upon F2. Here we substitute the value. We obtain the power of this combination of two lenses. So power is minus 0.75 diopter. Clear it? Okay. Later this numerical with the question in separate notebook. So at the time for preparation, so you can easily refer it, right?